Have you ever wondered how big the entire universe is? The visible universe is unimaginably huge, but there is one image that can give us a small glimpse at its awe-inspiring scale, and that is the Hubble Deep Field image. In 1995, astronomers wanted to see what would happen if they pointed the new Hubble Space Telescope at an area of the sky that was nearly devoid of all stars. They let it soak up light for over 140 hours over a span of 10 days, and what they saw was nothing short of spectacular. This is the Hubble Deep Field image. What you're seeing here is not just a few stars, nebulas, and star clusters, but each and every dot and fuzzy patch you are seeing is an entire galaxy, each containing around 100 billion stars. To get an idea of how many stars are in each one of those galaxies, imagine an Olympic-sized swimming pool and fill it with standard 1.5 centimeter marbles. If my calculations are correct, taking into account the max density of close-packed spheres, it would fit around 1 billion marbles. That would mean we need 100 Olympic-sized swimming pools full of marbles to equal the number of stars in an average galaxy. In a similar, more recent capture called the Hubble Ultra Deep Field image, we can see around 10,000 galaxies, each with around 100 billion stars. Pretty cool, right? But you haven't heard the most amazing thing yet. This image is not the entire sky. Far from it. This is only a tiny fraction of the sky, 113 millionth to be exact. The Hubble Space Telescope is famous for piercing the limits of the observable universe, capturing light from ancient galaxies and stellar nurseries billions of light-years away. Yet this orbital observatory was never designed to look at objects inside our own solar system. NASA typically relies on dedicated hardware-specific probes, like Voyager, to study our neighboring planets. But these missions are often brief, capturing isolated data during a single high-speed flyby. Because our planetary neighborhood vast and constantly shifting, relying solely on those fleeting encounters leaves a massive blind spot in our ongoing observations. To fill that void, astronomers turned Hubble into a permanent watchman for our own cosmic backyard.
This shift transformed Hubble into a high-powered, long-term climate monitor for planetary atmospheres. On Mars, it actively tracks planet-wide dust storms. By documenting these weather patterns, Hubble builds a reliable atmospheric catalog that helps predict conditions on the surface, keeping our active rovers safe from sudden blinding squalls. Its gaze extends much further out, too.
On the ice giants Uranus and Neptune, Hubble routinely watches massive cloud caps develop, and it tracks dark, swirling storms that span thousands of miles. Since the last probe flew past those outer planets in 1989, these dynamic weather events have been completely out of reach of any other spacecraft. Without this continuous monitoring, Arjai Dovya Oldalitz of Lionel Fritjusev Limef inciting or of Tin. Amura of planetary weather would be limited to isolated snapshots instead of an evolving climate record. Beyond acting as a weather satellite, Hubble wields a specific technical capability, observing space in both visible and ultraviolet light. This diagram isolates ultraviolet and visible light channels. In ultraviolet, Hubble discovered Jupiter's massive auroras and a data spike, revealing water plumes erupting from Europa's hidden ocean. Switching to visible light reveals salt across Europa's surface, a geological indicator infrared probes completely missed. Analyzing planets across these specific, varied light bands exposes atmospheric and geological structures that single-spectrum probes overlook entirely. This constant multi-spectrum vigilance also allows Hubble to catch unpredictable, violent anomalies in real time. In 1994, it documented comet Shoemaker-Levy 9 colliding with Jupiter. This technical image displays the separated red fragments trailing through space, proving the object was wrapped apart by tidal forces before slamming into the gas giant and leaving atmospheric scars the size of Earth. Deep in the asteroid belt, it captured a bizarre X-shaped debris pattern trailing an object known as P2010A2. This specific structure provided rare direct proof of two asteroids crashing into each other, creating a debris trail that mimics a comet's tail. That immense optical resolution is also used to find debris hiding in plain sight. Hubble spotted a tiny, fragmented moon named Hippocamp orbiting Neptune, and identified numerous small moons tugging on dwarf planets way out in the icy Kuiper belt. These documented impacts and fractured moons highlight a solar system defined by chaos and violent activity, where objects are constantly colliding and breaking apart. Hubble now functions as a real-time mirror, reflecting the current state of our own solar system. Expanding its role beyond its primary mission to observe the ancient universe today, the James Webb Space Telescope often dominates the headlines for deep space discovery, utilizing its massive gold hexagonal mirrors to gather faint infrared light. But Webb's infrared dominance doesn't render over-technology obsolete. Hubble's unique ability to view local planets in visible and ultraviolet light makes it an irreplaceable complementary tool. Pushing the boundaries of astronomical exploration doesn't always require looking billions of light-years into the past. Some of the most chaotic and scientifically vital discoveries happen right here in our cosmic backyard, as long as we keep a lens trained on them. The Hubble Deep Field images allow us to peer deeper into space and time than we have ever seen before. I say deeper into time because some of these objects are so far away. The light coming from them has taken up to 13 billion years to get to us, so we're seeing them as they looked less than 1 billion years after the Big Bang, long before the Earth was even formed. Some of these distant objects are called quasars, which are the most powerful and luminous objects in the universe. Even though they're only about the size of our solar system, they emit up to 1,000 times more energy than the entire Milky Way galaxy, which contains between 200 and 400 billion stars. They're made up of supermassive black holes that are consuming so much material that they shoot giant jets of particles traveling at nearly the speed of light, thousands of light-years into space. Yeah, quasars are pretty awesome. Looking at this image is a humbling experience. But to me, it just shows how amazing our universe is and how much there is left for us to explore. It's almost unfathomable that we could be the only life in this vast universe. Peer into this image long enough, and you'll start to imagine what awe-inspiring wonders could be hiding in those distant galaxies full of billions of planets. Scientists are learning more about our universe and our local galaxy every day. Just imagine what they might find next.